So this is cable, this is point A, this is point B. I intentionally draw horizontal line here, so theta is 0 here, and a vertical line here. Theta is pi over 2, and we have a point like point C somewhere in the middle. So this is point C, this is theta. Can I say the tangent force for the cable at point A is equal to tangent force at point B is equal to tangent force at point C?
Yes.
No.
No.
This was something you did in statics. Remember, in statics, your cable was not under any load. But it is under the load. Concentrated load, uniformly distributed load. So they are not the same. And if you remember, we proved an equation. If you look at your note, we proved an equation to find the tensile force in the cable based on the coordinates of the points. And this was exactly the last term I mentioned before I leave the class, the previous class. So yes, they are not the same. So, and you know theta at point A is not the same as theta at point B, is not the same as theta at point C. But something is the same. And what was your name?
Clement.
Clement. This was his question. He said, the horizontal component of the force is the same, which is correct. The horizontal component of the force, we showed it with FH, and it was T times cosine theta. Do you remember? But this is for each specific point located on the cable. For example, for point A, or you can say that for point B, or you can say that for point C. This is constant, but so these are equal, but tangent is not equal, and theta is not equal. Any question? You should review the content once a week. I don't say every single session, but once a week, review the content of past 2 sessions to get updated. Another thing is that why, it was a question from him at the end of the class, why the horizontal component is constant. I proved it, but I think I did it at Roche, so I do it again. So consider a segment of your cable. This is a segment, I call it D, and I don't want to make it vertical. So let's call it E. So point D and E. There is a load on the cable. Remember, whatever cable we discussed in this chapter are under a load. Doesn't matter, concentrated load, distributed load, self-weight, etc. This is FH at point D, horizontal component of force at point D, and this is FH at point E, horizontal component of force at point E. Is there any other horizontal force applied on this segment? Remember, we have uniformly distributed load, but that is vertical. So if I write sigma fx, then we only have these 2 horizontal components, and they have to be the same. They have to be equal in magnitude, opposite in direction. So from here we can say the horizontal component at point D and point E are the same. So this is the way mathematically we can prove that the horizontal component of the tensile force in the cable is constant. And it is important. We already generated some formulas, so if you look at your notes. We are going to use them today. So I will not prove them again because you have the proof on your note. So if you forget the proof, go and read. But now, today, because we use those formulas, you can just have a look to make sure you have those formulas with the proof, and later you can review the proof. The textbook is the same. The textbook also uses those formulas. We solved a problem, and we just, it was problem example 5.2. Because I have doubt, you review the content. I told you to go and read the PDF file in Brightspace. I have doubt. Some of you do it, so I am going to quickly review that. So if you remember, this was the cable. So you have it on your note. So you just need to look at it. You don't need to draw it because you already have it. And this was X and Y. And this is X prime. This is 100 minus X prime. So we have point C, we have point B, we have point A. We already proved this. So if you look at your note, X prime was found 41.42 feet, and we found horizontal component of the force in the cable 36,459.2 pounds. This is what we found in previous session. Then I told you that there is a formula for Txy. That formula is, we already proved. So this is one of the formulas that we already proved. So you just accept it, later go back to your note and review the proof. At the end of the session, I told you that we have X for point A, we have X for point C, for point B and C. Substitute XA, XB, and XC here, and then you find T. Because the question is asking to find T at point A, B, and C, the tensile force. So this is the formula, and you just need to substitute X. So I do it for T at point A. For point A, negative 100 minus X prime, which is 41.42. I'm just using this coordinate system, and 100 minus X prime. So X prime is already here, we have it. So from here, XA is negative 58.58 feet. Okay, so we have X for point A. Then tangent at point A is, I'm just using this formula. So FH is 36,459.2 plus 850 times negative 58.58 square. 61, so the answer is 61,713 pound. We convert it to kip is 61.7 kip. So this is TA. Any question? So there are a bunch of formulas we already proved. If you use them, you can simply solve the question for homework, etc. And then we repeat this process for point B. X for point B is 0 because point B is just the origin. So T at point B is already FH. It is the horizontal component, and it is the minimum tensile force because point B is the lowest point. Remember, the highest point gives us the maximum tensile force, the lowest point gives us the minimum tensile force. Because point B has a horizontal tangent line, then point B is just the minimum and is horizontal component. So point B doesn't have vertical component of tensile force. Do you agree? Because if you draw a tangent line at point B, there is only horizontal component. And remember, the way you draw the tensile force it was one of the assumptions at the beginning of this chapter. We said we just draw a tangent line at a point that is T. So if you want to draw tensile force here, just draw a tangent line. So if you draw a tangent line at point B, that would be just horizontal. So tensile force at point B is just horizontal. It doesn't have vertical reaction or vertical component. So tensile force at point B is FH. Do you agree? Because at point B we don't have a vertical component. The way you look at me is like, okay, somebody must help. Because you are quiet, but I can see your eyes. Braden, help. Why the tensile force at point B doesn't have a vertical component? It just has horizontal component. So this is, so I draw it here.
Because if you break it down into its form, it doesn't have, it only carries force along the tangent line, and there's
Yes.
no vertical tangent.
So basically you say if we draw a tangent line, that tangent line has to be horizontal. Do you agree? So you don't have a vertical reaction. So the entire tensile force at point B is the horizontal component. So it is shown by FH, and of course it is the minimum because this is the lowest point. Any question? I think you still need to. When we talk about the horizontal component is T times cosine theta, always. So when you move from point A to B, T is changed because TA is not equal to TB. Theta is changed. But multiplication of T times cosine theta is constant. So you move until point B. When you reach to point B, then T times cosine theta is just this horizontal component. It means we don't have a vertical component. So point B is the minimum, which is horizontal. And then if you want to find the amount of tangent at point B, we follow the same formula which is here. And at point B, so we already have the amount of FH. Do you agree? We found it. It's here. We already found it in previous class. So I just write FH, which is 36. That's it. So this is the force, the tangent force at point B. Now, for point C, how much is x for point C? It is x prime, and it is actually x prime. We found it 41.4 42 feet. So from here, tangent at point C So now we have FH, which is 36,459.2. We have omega times X, which is omega is given, and X is 41.42. So from here, it is 56.83 pound. We convert it to kilo. So 50 times 7 kilo. So we found the tensile force at point A, B, and C, and they are not the same. So remember, the tensile force is different because the cable is under the load. You have the PDF file. In the PDF file, I provide alternative solution because the textbook actually uses two alternative solutions. So it may be confusing, but both of them yields the same result. So let's look at the alternative solution. Alternative solution for TA, for TB, and TC is basically the same, but the way we use the formulas is different. The textbook uses this formula: tangent of theta is dy over dx. So you already know this formula on the note, and then he said it is omega x over fh. So you have this, and you can look at this to see how it was derived. So we are going to use this formula to find TA, TB, and TC. So this is the way. We calculate tangent of theta for point A. It is omega xa divided by fh. Omega is this, xa is negative 58. So from here, it is tangent of theta A is negative 1.366. Using calculator, you find theta A, which is negative 53.79. So it means if you draw a tangent line at point A, this angle is the one that we say negative 53. So be careful about the sign, because sometimes you calculate this angle. Just be careful about the geometry. And then remember FH, the horizontal component was T times cosine theta for all points. It doesn't matter point A, B, or C. So I would say, for example, point A. Then from here, T for point A is FH divided by cosine theta A. We already have FH, which is 36,459.2. Cosine of negative 53.79. And then from here, TA is 61.7.
or
So this is alternative method. The textbook mostly uses this method, but I feel this is more straightforward. You want to find tangent, use this formula for any point. But both of them are correct. They can be converted together. So if you look at the proof for this equation and this, then you can see they can be converted together. So this was for point A. In the same manner, we calculated for point B and point C. In the same manner. The only thing you change is you find theta for point B, so you need to use x for point B. This is the only thing is changed. Then theta for point B, you find theta for point B, you find theta for point B, you find tangent at point A. Just change A with B. That's it. And repeat the process. When it comes to point C, just repeat the same process. That's it. And you have the solution on the PDF file. So later, verify your answer with the PDF file. Question? Any? Yes?
If you used x for point B, wouldn't it be 0?
Yes. And then he said, I don't know, I keep forgetting your name.
Race.
Race. He said, for point B, x is 0. So he said when we substitute 0, then tangent of theta is 0. Then theta B is 0. Yes. Theta for horizontal line, tangent line at point B is 0. Yes. So theta is 0. Cosine 0 is 1. And then FH is equal to TB times 1. Yes, we already know that. FH is equal to TB. Yeah. So basically, these equations are very close. From one equation, you can reach to another equation. This chapter is not difficult. You just need to practice a couple of examples. Originally, it was part of statics. When I was at your age, this was part of statics book. Then they moved it to structure analysis. And now it is part of our course outcome, so we have to cover it in this course because we follow the course outcome. Okay, if there is no question, I'm going to move to complicated problems within the textbook. Okay, I want to erase it, right? Okay. There is a problem in the textbook, page 198, example 5.3. So problem 5.3, this is not the end of the chapter, this is in the text. We have two trusses. So this is one truss, they are exactly the same. I tried to draw it nicely, but you have this figure in the textbook. So this point is a pin. It is important. And I intentionally changed it. This is a roller. Because when you look at the figure in the textbook, it's not clear. But now I'm telling you this is a roller. Point A is a pin support. The way we have this truss is like this. We have 4 at 3, which is 12 meter. 4 at 3, which is 12 meter. It means the span for truss is 3 meter, 3 meter. There is a cable. I use highlighted green for the cable. So the minimum point for the cable is at point. So let me call them A, F, G. This is A, this is F, this is G, this is C, E, this point, D, E, B. There is a force 50 kilonewton here. This point is I, this point is H. So the green color one is actually a cable. And eventually the cable is just attached to the ground from here. Something like this. I use brown color for the ground. This is ground. And we have a river. Basically, this is a bridge over a river. So I use, these are water. So basically, this is water. So 2 trusses are actually sitting on the ground like this. So this is the ground, but this here is the river, and it is a bridge. Okay. The reason I draw it here is that I just want to grab your attention for the details of this figure, because if I just show it to you, you just see and you don't look at the details. So now you see the dimensions, whatever. Okay, now, did you understand the concept? So here is just a river. 2 trusses, this is pin, this is support on the one side of the river, the ground, river, and here we have a cable, and the cable is actually holding this like this. The cable is holding these trusses. If there is no attachment between the cable and the truss, then the truss will fall down. So the intention of using the cable is just to hold these 2 trusses. Okay. And again, point C is a pin. If point C is not a pin, we cannot solve this problem. It would be indeterminate, and we cannot use the normal equations for that. So point C must be a pin. And the textbook also mentioned it. The textbook says point C is a pin. So now, the suspension bridge shown here is constructed using two trusses that are pin connected at their ends at point C, and they are supported by a pin at point A and a roller support at point B. Determine the maximum tension in cable from from I to H. So the cable from I to H, it has a tension. Let's call it T here. I want to call it, for example, T1. I want to call it T2. I want to call it T3. One of them is maximum. Remember, the tension is not the same. Forget about statics, because this cable is under the load. Now, what load is applied to this cable? Is it basically, I expected you to say that, because you have point load here, point load here, point load here, point load, point load. But we assume this is a uniformly distributed load, which is the self-weight of the trusses going through the cable. So if I want to draw this cable here from I to H, there are actually more and more. So, because they want to stabilize it. So in this case, because there are many attached points, we can say it's a uniformly distributed load applied to the cable. That uniform distributed load comes from trusses, the self-weight of trusses, as well as the vehicles. There are vehicles moving on the bridge, etc. So for now, there is no vehicle. So the self-weight of these two trusses are applied to this. We assume, because the textbook, I'm not sure if the textbook mentioned it or not, we assume that distributed load is uniform. Because you can argue saying that no, it's not uniform. For example, maybe here is heavier than here because here is a gap. Yes, but we assume it is a uniform distributed load. If not, then we cannot use our equation. So these are all the assumptions. And again, this example is within the text. So now we start the solution. Is there any question? So far I have been trying to give you the details of it. So now you know this is a bridge, the cable, the load is not concentrated load, it is uniformly distributed load, we assume it is uniform. So now, to solve this, the first step is problem solving skills. Usually we need to find FH. In most cases, FH is the component of the tensile force and it's always constant. So if you find FH, then you can solve many of the equations. To find FH, there are two steps. First step, draw the free body diagram for the entire structure. So I consider this is IH and I consider there are two trusses and this is BY this is point B. Remember, point B is a roller, so it has just one reaction. Point A is a pin, so we have AX, AY. When it comes to and then they are attached together. So basically they are one system. This is the free body diagram for the entire system, including cable and trusses. When you draw the free body diagram, you detach your structure from all the surroundings. So I detach it from the ground, I detach it from the ground. What else I need to detach? What point I need to detach? Here and here. I detach them from the two posts here. There are two vertical posts, I detach them. So you use a knife and you just cut your system from all the surroundings. So there is something here, reaction. So of course you have FH, the horizontal one, and you have, of course, the vertical one, HY, IY, and the vertical one. Any questions so far? You know this is HY, you know this is IY, you know this is FH, the horizontal component. What should I put here? The horizontal. Do you agree FH is constant through the entire cable? The horizontal. So why not I just use the same symbol, because they are the same. FH, horizontal. So this will help, because this is the free body diagram for your structure, and then we have one more force. It is given 50 kilonewton. That's it. This is the free body diagram for the entire system. Any question? So now, we take a moment about point B. Sigma M about point B. I assume the conventional sign to be counterclockwise. So when I take a moment about point B, there are some forces removed. By doesn't produce any moment about point B. Ax doesn't produce any moment about point B. Alex, why? Why Ax doesn't produce any moment about point B?
Because they're on.
Because the extension is passing, line of action. Okay. What about Hy? Hy is the same. Hy, the extension of Hy passes through point B. What about Fh?
Will they cancel?
Yes, they produce moment, but they cancel each other because Fh times this distance and Fh times this distance will cancel each other. They have different opposite direction. So we don't need to write them. So what we need to write is, we have Ay times the distance,
24.
Ay
It's 12 and 12.
is, it is clockwise, right?
So it'd be, yeah, negative.
Yes?
Negative.
So we say negative Ay because it is clockwise. But I just want to combine them together. Ay times how much?
Negative 24, or sorry, 24.
24. What about Iy?
Be added to AY.
Yeah, because Iy is the same direction and it has the same distance. So we just add them together times 24. Negative, and what else we have? Hy.
No. C.
See?
We have the C.
Yeah, so Hy doesn't produce any moment, so
The point,
C.
or not the point at C, sorry, the one off from, yeah.
This one.
50, yeah.
Yes, 50 kilonewton. So 50 kilonewton is,
Be positive, that's 9 meters.
negative, yes, positive, plus 50 times, the distance is actually here, it is 9, yes, because there are 3 here. 1, 2, 3, so 3 times 3 is 9. Each span is 3 meters, 4 at 3. So it's basically 3 times 3. So this distance is 9. Okay. Equal to 0. From here, ay plus iy is calculated 18.75 kilonewton. Okay. So we have found one equation so far. And this example is not easy. That's why I'm just going through it. So we still need some more equations. The next part, I just write it here at the top. We draw the free body diagram for half of this structure. So it means we just cut this structure right in the axis of pin. Remember, pin is important. If we don't have a pin here, then this structure is indeterminate. So we just disassemble this structure. It means we separate two trusses at point C, and I write Cx, Cy, and when it comes to AY, AX, and we have a cable like this, but just half. This is FH, this is FH, and this is IY. So we have IY, we have FH. What else? This distance is 6 meters. And this distance, if you look at the figure, is 14 meters. And this distance is 12. This is the free body diagram for half of the structure, the left side of the structure, when we detach it from the pin at point C. So the free body diagram is there. Raise why I do not put a vertical reaction at this point.
Because there's only a horizontal component.
Yeah, there's only horizontal component. Yes.
Is the moments about the equation?
Yeah,
Yeah.
it is
Isn't
about point B.
Yeah, isn't IY 14 meters from the line of action of the moment?
No, because it's, you have to look at what it's perpendicular to. The line of action of the moment would be perpendicular to it.
Well,
IY and AY are on the same, they're the same horizontal distance, and since
Oh.
they're,
That's why we add them together. But you can separate them and later add them
yeah,
together.
okay.
So this one is the free body diagram for half of the structure. Do you agree? So this is pin C. We are going to take advantage of pin C. Remember, structure determinacy, pin was always helpful. It gives us one condition equation. So now we are going to take advantage of that. That condition equation means moment at this point is 0. So now, what point shall I take moment? I am going to take a moment about point C. Sigma m about point C is 0. And then this one I write, Race said this is 0. Okay. The conventional sign is assumed to be counterclockwise. Okay, Cx is removed, Cy is removed. Ax, if I ask this from Alex, she says AX extension passes through point C. So it doesn't produce any moment. So now I write AY, again AY and IY in the same manner Nana asked. They produce a moment clockwise. So I need to put a negative sign here. Times 12. Times 12. And then I have FH at the left side. I have FH at the right side. The one at the right side is FH times 6. At the left side is FH times 14. Now they don't cancel each other because Braden is thinking they cancel again, but they have different distances that the moment produced by them is subtracted. Yes?
I think you have them backwards.
Positive, negative, negative.
Okay. So the conventional sign. Which one is negative?
The 6.
This one, okay. Yes, it's negative and that one is okay. So from here, AY plus IY is equal to FH times basically 2/3 times FH. If you simplify. So far we have two equations. Equation number 1, equation number 2. But we have 3 unknowns. And I leave it to you guys to use your innovation and tell me what can you extract out of these two equations.
You can set 18.75 equal to the 2/3 FH and solve for
That's
FH.
it. So you can find FH. That's it. Okay, and this is what we need, FH. Okay. So I'm going to, so FH is found from equation 1 and 2. FH is 28.125 kilonewton. I'm going to erase this part, so take a note. Then, because I want to keep this figure. Take a note and then. Basically, this was the challenging question in this chapter, and I wanted to go through it with enough time to make sure you understand it. The rest are normal. And this is the practical one. So the other book is trying to bring a question which is somehow resembling this real case scenario from bridge, etc. But remember, there are some assumptions. The distributed load over the cable is assumed to be uniform, but in reality it's not 100% uniform. Okay, I erase it. So we have FH. The next step is finding omega. We don't have it, right? It is not given. There is an equation used for the shape of the cable, and we already proved that equation. We proved it in previous class. If you have one point out of your cable, It means if you have x and y, you just substitute those points. So I'm going to use a point for this, and that is point I. Let's try it. How much is x and how much is y if we assume the lower point, what color? Blue. If we assume this is x and this is y. How much is x for point I? How much? How much? Yes.
12.
Yes. Why you 12? But some people like argue and they say negative 12. Okay. Negative. Because it is at left side. How much is y for point I? Is it positive or negative? Positive. So now I'm going to substitute this point into this equation. And we already know FH has a value. We calculate. So y is 8, positive. Omega is unknown. X is negative. FH was how much? From your note, 28, 1.2. From here, you use your calculator and you find omega 0. The value for omega is 3.125 kilonewton. 3.125 kilonewton. Any questions so far? So we have FH, we have omega. What was question about? The question was asking to find the maximum tensile force in this cable. This was the objective. As an engineer, you want to know how much is the maximum force in the cable so that you purchase a good cable with that. So that you go for enough thickness of cable, material, etc. so that the cable can sustain that maximum force. What equation do you use? If you look at the previous example, we had a formula and we proved this one. So if you don't remember the proof, it is on your note from previous section. The textbook also uses this formula directly, but we already proved it. So later you can look at the proof. The maximum is this one. But I have doubt if you go through it, so I want to prove it now. I want to make sure you know everything, even we already proved it. So I go back and write that again as a reminder. Basically, we said Txy is T sine theta square plus T cosine theta square. I'm sure you agree with this. Then we said T sine is omega x. T times cosine is FH, the horizontal component. Now, we are going to find T max. Basically, the maximum of the tangent goes to the highest point of the cable. Do you agree, Race? So it means point I and point H. They are maximum. So what point is the minimum tangent? Selena. I call it C, I call it H. Which one is C? Because it's the lowest point. So now if you want to find T maximum, you must go for I or H. Okay. So omega is 3.125. And then X, how much is X for point I? Negative 12. Omega X squared. And then FH already calculated because we have FH in this problem. We just substitute it. How much was FH?
28.125 kilonewtons.
Say again, 3?
28.125 kilonewtons.
Okay. That's it. Because FH is constant, it doesn't matter which point, I or J. The only thing which is varied is X. And we go for highest point. From here you can find the maximum of the tangent. But the textbook is using the other formula which was derived in the text. But this is the direct one because I want you to just understand what you're doing. But it's up to you. You can include that formula in your crib sheet in the exam. So this is how we find it. T max. 46. T max. For example, T minimum, Selena said at this point. Then you use the coordinates for this point, and then Race says that X is 0 here, yes. So basically, T at this point is FH. So you don't need to calculate T minimum. That's it. Could you do a favor? Calculate. I just want to make sure this is equal to this. And this one is equal to this. Because it is? Okay. All right. Any question? Let's look at the time. We still have 14 minutes time, so we can solve one more problems. And you have the PDF file. So all of this information in short are in the PDF file, so you can have a look on the PDF file. The next problem is end of the chapter, problem 5.8. Yes?
Does the 50 kilonewtons between C and B not have an effect on T max at all?
You say this one doesn't have effect on T maximum?
Would it not?
No, it has effect. Because this is the only force applied on this bridge, so definitely it has effect. But you don't see the direct effect. So basically you are asking where I can see the effect of this. So chase the formula and find something. Let's look at this. T maximum is composed of omega. Do you agree when I increase 50 kilonewton, omega will be increased? Yes. So it has an effect, but you cannot see here. It is through other parameters. So basically he said if I double it, for example, the final answer will change. Yes, the final answer will change. Yes.
W naught, is it a function of, is it kilonewtons per meter or is it just kilonewtons?
What we found here, W is kilonewton, is kilonewton per meter. Yes, I forgot to. Yeah, because it is distributed load over the projected length.
And then the second question is, if it's distributed across the distance, would it be 24 instead of 12?
No, it is W times X. This is X. X, this was the question from Selena. Selena said point I gives us the highest. Basically, this is X coordinate for point I. Do you agree?
Based on our lowest point, and our lowest
Hmm.
point is 12 meters off from that. So you don't take it based on the entire length of it, you take it based on the lowest point.
And look at here, this is the origin, right? So from here to here is 12. The coordinate, not the entire length span.
So force on I is not affected by the other half at all. It's kind of split in half on both sides.
I wonder from these kind of questions, I just look at the calculation. You should not try to see, I mean, the question, does it affect this or does it affect this? When you design a building, there are thousands of parameters. You just go through the process. You don't want to see if this one affects this because then you get crazy. It's not possible. Sometimes it's easy, so look at the process and tell me which part is not clear. You know what I mean? Because sometimes there are a lot of variables, so you should not spend, it's possible, but you should not do this. But now again, say your question.
So the weight, it's the same on like I side and the H side?
Okay, I side is here, H side is here. What do you mean by the weight? You mean omega?
So omega not, so it's only times 12 because I is carrying half.
It's on. It's no. It's times 12 because this is X coordinate for point I. You know what I mean?
Not distance.
No, not this. Not this. In this formula, X is the coordinate for the point. Maybe Race says I want to use the coordinate for point for this point. How much is X for this point? Okay. Race says this is 0. Then T is equal to FH, of course. So it's a coordinate. Maybe you want to use X for this point. Then X is measured from here to here and then substitute. The reason you ask this kind of question is, of course, because these are new for you. So I recommend you to look at the proof of these equations, then you will understand. For example, he said, okay, y, X is the coordinate. Right? Then you need to look at the proof of this. Then you understand why it is the coordinate, it's not the distance, this kind of thing. Well, it's normal for the first time when you see this. And to me, this chapter is not difficult compared to other chapters. We go to other chapters like inference line, there are plenty of, there are variety of questions. Then you have to try them. But this is the most difficult question in this chapter. Yeah. Okay, next question. Let me see, we still have like 10 minutes. So I'm going to erase this. And hopefully we can manage that. That question is not difficult. By the way, you can include all of the formulas in your crib sheet and use them. So it doesn't matter. The question said, there is a pin support. Point A, there is another pin support. Point B, we connect them together by a cable. The cable is under uniformly distributed load.
It be the same height or
What?
are they the same height?
Yes, that's a good question. A and B are on the same height. And the problem is, end of the chapter, problem 5.8, so later you can check the nice figure in the textbook. Problem chapter 5, problem number 8. So this distance is given 10 feet, and this distance is given 20 feet. Oh, so it means my drawing is not to the scale. Okay. Yeah. The question says, this cable is subjected to a uniformly distributed load. Omega is given in this question, 200 pound per foot. Determine the maximum and minimum tension force in this cable. So the question is asking for T max and T min. There are alternative solutions. I just use one of them. We assume this is the origin. Usually we go for the lowest point. So I assume this is X in orange color, and this is Y. Okay? Usually we go for the lowest. The equation for the shape of the cable is always this one, and we already proved this equation. So X for point B and Y for point B are here. X for point B is 50 feet, Y for point B is 20 feet.
50. Is it a 100-foot cable?
Let me check. Oh, yes. So my drawing is, yes, sorry. This is 100, so revise it. The total span is 100. Yeah. So it's 50, 20. I just substitute these coordinates into the equation, and I find omega. So Y is 20, omega is given 200, FH is unknown, X is 50. So from here, I can find FH. FH is one of the key parameters. 12500 pound. We convert it to kip, 12.5 kip. So we have FH. And next step, T minimum is for the lowest part of the cable, and it is equal to FH, which is 12.5. So we don't need to discuss why T minimum is FH, because we already discussed. This was my discussion with Race. The lowest part of the cable is T minimum, and it has only the horizontal component. So we already have the minimum tension in the cable. So now we are looking for maximum. There are alternative solutions. I intentionally use another method that we never used, so you can see that. We are going to find theta at point A, because we know point A and point B are the highest point, so they give us the maximum. So doesn't matter A or B, this is dy over dx and omega x over 2fh. Let me look at the formula. F omega x divided by fh. So from here, omega is 200. X for point A, I am going to use point B because it's easier. Then X is positive, so I don't want to confuse you. So X for point B is plus 50, and FH is 12,500. So from here, theta at point B is found, 38.66. The reason we use point A and B is because they are the highest point. So we find theta at point B, and then we know that FH is T times cosine theta, for example, for point B. And then from here, we find TB, which is FH divided by cosine theta B. FH is, so from here, $12.5 kip. T at point B is 16.0 kip. And remember, T at point B is T maximum because point B is the highest point.